Good morning, everybody. It's glad to see everybody got out of bed. I hope everybody had a good time at the party last night. It was a good time. We're going to launch right in and entertain ourselves a little bit of security early in the morning. So here's the real challenge. At the heart of this whole infrastructure is what we need to have is a known user on a known device with a device that's in a known condition, creating an assured instruction. And I'm going to use the word instruction pretty broadly through my conversation this morning because that's what payments do. We're not doing transactions on the phone. We do transactions out on the distributed network. What we send are instructions. If the instruction is altered, then we have no idea, a false transaction gets done. And so one of the real challenges we have in blockchain today for all aspects, whether it's assets or money or Bitcoin or a variety of different things, we don't have a real strong understanding on the blockchain of whether the user intended to do the transaction. We know this key was used. What we don't have are any cybersecurity controls that assure that the user intended this transaction. So what's fun is we have some new toys to play with. Blockchain is an incredible piece of distributed infrastructure to enable us to store a ledger of facts. It provides a persistent and consistent recording of the events that took place. However, if we send garbage to the blockchain, it's going to permanently store the garbage for all time. And so, while it's interesting to talk about the security of blockchain, I would argue that that's actually, while interesting and important, not the critical item. The critical item is we have to make sure we also assure the instructions. If you talk to the rest of the payment industry, they don't talk about the security of the back office. That's not where the hacks take place. They talk about the security of the point of sale terminal. So we have another piece of the puzzle. Trusted Execution Environment, or what's called TEE, is a set of technologies that have been standardized by a combination of the PC industry and the payments industry, two standards bodies, the Trusted Computing Group and Global Platform. And today, literally billions of devices have been shipped with the hardware security built in. What we need to do is put it to use. So it's not about shipping cards, although the original specifications were all around smart cards. This is about having that security built into all the mobile devices. So today, as an example, Rivetz software that we're building is compatible with just over 500 million phones already in the marketplace. So I said before, the ledger is safe. The instructions are not. If we were to take all the best minds at this conference in blockchain and have them rebuild the SWIFT network, we would think that's a cool project. However, the Bangladesh bank hack where they stole $100 million would still work perfectly. They stole the keys. They stole the keys to SWIFT. And they sent false transactions. And the only reason they got caught, by the way, you'd never catch this in a distributed network, they got caught because they spelled the name of the bank wrong when they were transferring it. And one of the humans in the process realized that they'd spelled the name wrong and thought that was interesting and made a phone call. And so they only stole $80 million instead of $100 million. By the way, this is going on regularly. It's literally billions of dollars of fraud that's going on. So I find this helps. I had the wonderful opportunity a number of years ago to have a guy who was working for me who was the M in EMV. He was actually the MasterCard rep who had gone to all of the EMV original standards meetings in the late 80s, early 90s. And he brought along his friend who was then working at American Express, who was the E in EMV. And I spent an entire afternoon in my office with E and M in my office explaining to me what EMV was. And it was a really interesting and funny conversation. And what it turns out is nobody really knows. We think smart cards make EMV secure. Well, it turns out that 2 of the 3 components of security in EMV for point-of-sale payment terminals actually takes place in the point-of-sale device. And when EMV in their specifications talks about online, they don't mean the internet. They mean the point-of-sale terminals now online, because, of course, when first point-of-sale terminals came out, they were batch processed at the end of the day. And so it's so exciting that we can do transactions in real time instead of storing them for the whole day at the retailer. It was fascinating to understand that to this day, there's never been a secure EMV internet transaction. And I was involved at the time in helping to ship smart card slots. We shipped, I don't know, a few 100 million of them into the PC industry. And so the slots were there, but you can go to Paris and have an EMV card, a smart card that's been there working for 20 years, and you can buy a laptop with a smart card slot in it. You know what you can't do? Plug your card into the machine, do a transaction. It doesn't work. You have to use this old American scheme where you type the number on the front of the card in, and then you flip it over because that's security, and you type the number on the back, right? Because that way there's two sides of the secure transaction. So just understand, there has not yet been a secure e-commerce transaction. This whole Bitcoin thing is trying to protect a secure e-commerce transaction. You don't use any of the toys. So what is a transaction? Trusted display. What you see is what you sign. If the screen that you type the Bitcoin amounts into, like a browser, is not secured, there is absolutely no assurance that the software in your computer sent to the network the same transaction that you thought was shown on the screen. Just understand that all of your computers can and probably have been rooted by somebody else. And there's no way right now for you to test it. While we've built a lot of technologies in, nobody turns them on. So just assume your computer's from North Korea, and then ask how would you feel comfortable in doing a transaction for $100,000 or $1 million on that computer. Trusted input. So at some point I have to actually enter a PIN number or some mechanism of identifying me as the human. And so there has to be some way of collecting user intent. And so secure input is a really important piece of this puzzle as well. Trusted execution. So this is where we have isolated execution of the actual transaction within the device. And so this provides us a very strong mechanism to assure that the transaction actually executed happened within a safe space. Now, trusted execution is cool, and lots of people think like a smart card provides you with trusted execution. It actually signs the transaction inside the chip of the card. But I need the other two pieces to go with it. And so we think this is the whole pile, but it's really not. There's another piece. And so the other piece is we need some form of attestation and verification that that transaction was actually done on a device that has the capabilities of doing those three things. And were they working at the time? And so attestation is a really important component. You know this as a term called PCI compliance. What PCI compliance says is, hey, before you can have a point of sale terminal and just willy-nilly plug it in, it's got to be PCI compliant. And what that basically says is there's some form of certification that the trusted display and trusted input is working correctly, and that there's some test that it hasn't been modified. So we need all this running in a Bitcoin device. Well, so today, if you get a Trezor, or Ledger is showing a capability out there as well, you have the top three, you don't have the fourth. And so it's been interesting to look at how would we test. Let's see, a cryptographic hash is typically a good way to do attestation. Could a blockchain type transaction compare two hashes and make a decision? Well, that actually would be a pretty cool function because blockchain people know how to spell the word hash. So what we've done, and what I'll show this morning, is a short video of integrating device integrity and a Bitcoin instruction into a combined transaction so that what we'll demonstrate is cybersecurity controls on a peer-to-peer transaction that asserts that the state of the device was in a known condition with a known user when the transaction was executed. What we're doing is we have a device trusted execution environment running our software that does an internal integrity test. We then take that internal integrity test, we take it out to an external device, what we call the Rivetz attribute server. And we actually check to make sure, in the case of this Samsung phone, that the trusted execution environment is signed by the manufacturing keys that came from Samsung. So we can actually prove the supply chain integrity of that trusted execution environment, including the manufacturer, the root OS software, the BIOS, the application that's coming from Rivetz. We test a chain of hashes that are rolled up in a signature to a single signature that we call a reference health measurement. And then when a transaction goes forward, later on, after we've done all those checks, we can do a real-time test of the health. And if the real-time test doesn't match the reference test, it fails. Now, what was fun about this project was once we implemented it, we discovered the other thing we could do is check external attributes. And so this is the way we could check, geofencing, it would be trivial to check and say this is Bitcoin that's only spendable in Nevada. Trivial. Things like integrated KYC. So this wallet only works if your KYC test is active. There are some incredible things that are possible. It is important to note that this has really strong privacy characteristics because the reference is just a really big random number. It might be the same for 2 transactions. It doesn't have to be. It could be updated on a regular basis. Just showing you what's going on inside the device, there is an actual trusted execution environment where we run an app inside the secure world, the blue box. It talks to an app that runs in the normal world, which is where the actual Bitcoin transaction goes. And with that, I'm going to go one more. So this is a process that's one step at a time. At first, we can do simple things like 2-factor authentication, where I integrate a transaction into 2-factor authentication. You could add that to any existing online wallet today. The second step, and if somebody sees me after this, I can show it to you on the phones. It's a little hard to show in a video. But it's basically a secure instruction. So as I do a transaction, the service, like an online wallet, could send a transaction to my phone with secure display and ask me for a PIN number and confirm. And so I can have just the integration of a confirmation for an online wallet. And the third level is modify the blockchain and integrate the transaction directly into the blockchain. So let me show that to you now. If you guys backstage will click and start this. Oop. Go back one slide.
This is a demonstration of the Rivetz Bitcoin Health demonstration. We're using a blockchain, a Bitcoin transaction, and attestation of the health and integrity of the trusted execution environment. In order to show this demo, the first thing we do is we pair the attestation demo app with a Rivet. That actually creates the keys between the app and the trusted execution environment. And then the second thing we do is create a Bitcoin address. This actually does an internal integrity test of the device and creates a hash, not only of a pay to script hash, but also the health hash within the device. Now we're going to register that health hash. So we register the health hash with our Rivetz attribute registrar. It includes the hash and a number of the internal integrity controls within the device. And now ultimately we're going to fund funds into this attestation-based wallet. So in order to do that, we produce a QR code. We have a second device here. We'll scan the QR code. And we're using our own private chain, so as we send these funds, then it will transfer quite quickly. And we see the funds have been transferred to the device. So the next portion is to spend the money and send it back to the device, so we'll push spend. This creates a 2E-based confirmation. You can see the amount we're going to send and to the address, and we're going to push confirm. And that will actually cause the transaction to go back, and you'll hear the deposit of funds on the wallet device.
And that blue screen was a trusted display.
Oh, there it goes. So we've had success in the delivery of the funds back to the other wallet device. So now we're going to actually refund the wallet with money and demonstrate that if we break the transaction, if we break the health and integrity of the device, the transaction will fail. So we're resending funds. We have funds received now back. And so what we do is we actually make a small alteration to the internals of the system. So we've now changed the insides of the system. We'll go back to the wallet when we push spend money. Now as we spend the transaction, again, we get the 2E-based confirm. We confirm the transaction, and the transaction is rejected. In addition, you'll see that then there's a reason why the mandatory script verify flag was set. So it showed that the transaction failed because the health test did not compare properly. Thank you very much. This is an interesting demonstration of some of the most advanced cybersecurity controls for financial transactions between devices that's ever been done. Thank you.
So what's important about that is this is the context of, we showed this on a device, but this could show that Goldman Sachs did a transaction on the blockchain. and I can forensically prove what cyber controls were in place when they did that transaction. So this brings the other piece of security to the puzzle, which is how do we forensically prove the user who did the transaction had intent? And ultimately that their cybersecurity controls that are under their regime are put in place. So this is not a central service putting cybersecurity controls over a device. These are not Rivetz controls. We're just allowing the owner of the platform to put their own controls in place, and we're asking the blockchain to test for us that our controls are still in place as we intended. And so therefore, there's an automation of a real-time cybersecurity validation by the blockchain on every transaction. This was done by adding 2 opcodes to the blockchain, one of which was actually in the original blockchain and was taken out for security reasons and is in the process of being put back in. This demonstration was built on Blockstream's Elements chain. And so we believe that both the opcodes that we used are on the roadmap for the Bitcoin community to include in the standard Bitcoin blockchain, and will bring world-class cybersecurity validation for any and all hardware-based wallets to test to the health and integrity inside the wallet. What we need to do is we need to lead the industry, not follow the industry in cybersecurity. This is how we move to the next generation of e-commerce security. By the way, I think what you saw there would give you the beginnings of the answer to how you secure all of IoT. This is that an instruction sent to a medical pump to set the pump to 50 milliliters came from a known device in a known condition and can be forensically proven. So if there's an error and somebody dies, we can figure out who did it. And I think the other piece that's interesting in this is that there's real potential to use this in our daily lives for logging on to any of the cloud services that are out there. So happy to talk to anybody else about this further. I don't know if we have time for 1 or 2 questions, but happily would answer a couple questions if they want. One question.
Regarding intent, so I got the attestation and secured it, but doesn't really, how does that relate to the user intent?
Well, so in this case, in this demonstration, we did not set up a PIN number. We just had a confirm. It's impossible for the operating system and the phone to have pushed that confirm. So the person with presence of that platform had to push confirm. So once you have trusted input, one of the things it gives you is that I know some human was with that phone at that time. Now, what's interesting with phones is I obviously have a lot of other data to prove who had that phone with them at the time. Like if you were making phone calls all day and in between 2 phone calls you did a transaction, probably pretty sure I know where the phone was and who was with it. I actually would tell you that I think one of the core things to cybersecurity in this space is we don't need to get too fancy. Your smartphone is yours. And when you lose it, you know. And actually, I think that piece of cybersecurity is one of the most powerful things we can leverage to keep a very simple consumer experience and yet incredibly strong security. Our favorite 2-factor authentication is not biometrics, it's not taking selfies, it's not waving your phone around, it's dialing the number and pushing send. And take whatever you think you want to add in authentication to a device and tell me that you would use that device for dial the number and take a selfie or dial the number and swipe your fingerprint. No, you like dial the number and push send, and we've been able to train everybody in the world to it. Thank you very much. Thanks for your time. Hopefully I didn't put you to sleep first thing in the morning. Have a great day.